Okay. Um, Good. Welcome everybody to this session. It's great to see you, and I would like to thank the organizers for pulling this event, pulling off this event. I think it's been a great organization so far. It's a beautiful venue, and looking forward to the rest of it. So before I start, may I just ask all Argentina fans to raise your hands? Oh, wow. Okay, I'm indebted to you guys. Okay, so I was allowed to take a topic which is pretty broad, fundamental physics with galaxies, which more or less means the way I see it, that I can do anything I want. And but I will try to deal with this problem from a first principle attitude as much as I can. And the main reason is that galaxies are very complicated. They're complex objects, very nonlinear, highly n-body gravity systems that we need complicated simulations to really try to calculate. And so it is often, I find, lost in this complex problem. The basic lessons are kind of lost, at least on me and possibly on many others. So I'm going to try to take a step back, and I'm going to try to present this problem as simply as I can. Then the goal is that everybody understands it, whether you are working on inflation or whether you are a particle physicist, and perhaps even if you work on galaxies, there will be something interesting for you in what I will say. So I have fundamental physics in the title, and I'll talk about fundamental physics. And I guess the first question you need to ask yourself when you go to an astrophysics school and talk about fundamental physics is, what is really the connection between these complicated astrophysical systems and basic physics? And the connection is very, very deep, as you all know. So accelerator experiments, essentially, have delivered to us this standard model of particle physics, a quantum field theory, that describes quite successfully essentially everything we measure on the ground in terrestrial experiments. And there are thousands and thousands of different experiments and different quantities that we're testing at a vast array of energies. And all of them fall kind of neatly into this picture, apart from some questions and puzzles here and there. But this more or less works on the ground. Nevertheless, as you all know, the standard model has some deep, unopened questions that it does not address. And there are really many. I collected just a few of them. So completely obviously, it does not incorporate gravity in it, and the question of how to incorporate quantum field theory into a framework of gravity is an open question, maybe one of the most important questions of our time. So that's just a plain missing ingredient. It's simply not in the formalism. But there are also issues that looks like omissions that could be put into the formalism potentially without some radical change, but are not there in the standard model. Neutrino masses are one such a clear example. Dark matter is another. We see evidence for a missing mass, or gravity doesn't really behave the way we expect from luminous mass. We call this dark matter, and it's not in the standard model. It's not in the particle content of the standard model, whatever it is. Then there are questions that seem to be related to initial conditions of this system that look very weird. One of them is the initial condition that are usually attributed to cosmic inflation, the near scale invariance of initial perturbations and the super horizon correlations. There is, in the standard model, no clear mechanism to allow for inflation. There are discussions whether the Higgs field can be related to it. It is not completely clear as of yet, but it doesn't look like the standard model contains inflation in it. Then there is the asymmetry between baryons and antibaryons in the early universe, which cannot be addressed within the standard model. And there are many other questions that are deep and standing there. Some look like what seems like ad hoc fine-tuning from the point of view of this quantum field theory, and we don't know the answer for them. So all of these questions affect this model that we have, and we have been testing in collider and terrestrial experiments. But then, of course, if you have a Lagrangian, it supposedly should explain everything you see. That's the whole point of what we're doing here. We're trying to reduce the vast array, as large as possible, of physical objects that we see into a small number of rules or equations. We're trying to make reduction here. So the standard model of particle physics better explain everything we also see in the sky. And in fact, essentially all of these major open questions of the standard model have something to do with objects that are only accessed in astrophysics and astronomy. Just to give some example, neutrino masses, the evidence for neutrino mass was first found when people tried to calculate and then measure the flux of neutrinos from stars like our sun, specifically from our sun. Okay? So we try to understand how stars work by measuring neutrino flux from the core of stars. The measurement didn't agree with calculations. Eventually, it turned out that what was at fault here was not the astrophysics of the sun. What was at fault was, in fact, the standard model itself, which must be extended. And of course, there are many other examples. I try to list here very roughly how the astrophysical systems relate to these questions. Some questions were first discovered by looking at astrophysical data. Other questions are only detected when we look at astrophysical data. For example, dark matter. For example, vacuum energy, with the many questions attached to it. For example, initial conditions. But even questions related to gravity, for example, or why do the strong interactions don't contain large CP violation in them, even these questions have constraints on them that are imposed by our understanding of astrophysical data. For example, the question of CP violation by the strong interaction, beloved potential solution of this problem is the axion, the Pesce-Quinn axion. And axions are constrained, for example, by observations of core collapse supernova explosions. They are constrained by stellar isochrons when we measure the number of stars at different places on the Hertzsprung-Russell diagram, and so on and so forth. So everything here is deeply related to astrophysics and cosmology. And there is a reason for this. The reason is astrophysics and cosmology systems often test physical situations that are very, very difficult to test in the laboratory. Okay? Dark energy or vacuum energy, to test it, you've got to attain a vacuum that is absolutely enormous. You've got to clean everything out. Our universe, it just so happens, is an excellent vacuum chamber. And so, in fact, it is so vacant that the vacuum energy actually induces dynamical effects, and we can test it. Galaxies test tiny accelerations on the one hand, and then enormous amounts of mass on the other hand. And so they can test gravity on a whole different scale than we can do in terrestrial experiments. And so maybe it's not a shock that the theories that we have devised to address terrestrial experiments break down and fail when we apply them to a monster like this one. So there is a deep connection between astrophysics and fundamental physics, and I'm very happy to have my topic to discuss galaxies. So going to galaxies, I would like to start with perhaps one of the first essential fundamental lessons that humanity have found out by looking at galaxies. Anybody knows what this object is? Yes, it's a galaxy, but which one? Nobody knows? So this is Andromeda. Andromeda is a neighbor of the Milky Way galaxy. It has roughly similar properties to the Milky Way in terms of mass and morphology, etc. And it is so close that you can actually relatively easily see it with the naked eye or with a reasonable telescope or binoculars. Its size on the sky is not much different than the size of the moon on the sky. But it is, of course, much fainter because it is far away. So people have seen, they've been aware of Andromeda for thousands of years. In fact, there are records. There is a delay. Is it range? Yes, it's range. So there are records of observations of Andromeda dating back at least 1,000 years ago. This guy here is Al-Sufi, who recorded this in a book called the Book of Fixed Stars. He was somewhere in between an astronomer and an astrologer, I don't know how to say it. And he referred to Andromeda. But of course, 1,000 years ago, Al-Sufi and anybody else had no way of telling what this object is. This was just hanging in the sky. Everybody saw it. Nobody knew what it was for at least 1,000 years, simply because they didn't have the tools. In fact, so not range. In fact, even if you go back 100 years ago or so, 102 years ago, it was still not clear where Andromeda is and what Andromeda is, okay? And this was the basis of a big debate that was between astronomers that I'm showing here. It was called the Great Debate. The debate was, is Andromeda nearby and small, just a smudge of gas and stars maybe, in our Milky Way? Or could it be that Andromeda is enormous and enormously far away? The eternal question of astronomy, right? Curtis was saying that Andromeda is big and far, and Shapley was saying that Andromeda is near and small. And there was a fundamental question here, because the really question at stake was, how big is the universe? Right? Is the universe just limited to the stars and gas we see next to us in the Milky Way? Or could it be enormous and we're just a little island in it? Of course, Curtis was right. But I just wanted to comment that astronomers took their debates and their physics very seriously these days. So that's something that Curtis is quoted to have said. A friendly scrap is great. It kind of clears out the atmosphere. He was so serious about this. He actually mentions that they're going to use their shillelas to sort it out. I had to go to Wikipedia to see what shillela is. This is just how serious these people were about their astrophysics debates. So, unfortunately, these guys didn't actually get to use their shillelas to sort this out, because Edwin Hubble solved the problem. And he solved the problem by finding that there is a pulsating star in Andromeda, and a Cepheid, essentially. This was just 99 years ago. And pulsating stars like Cepheids, Hubble already knew at the time, they can behave as standard candles, because there is a calibration law. You can calibrate the period of pulsation of Cepheids is correlated with their absolute magnitude, or their total brightness. Brighter Cepheids, bigger stars, they take more time to pulsate. So if you can measure the pulsation time, the period, you have a decent estimate of the total luminosity. If you have the total luminosity and the observed luminosity, you have the distance, and so you can measure distances. And so Hubble found out and showed that Andromeda was of the order of millions of light years away from us, way outside of the Milky Way, and the universe was completely enormous. Now, I won't comment about it, but the next discovery of Hubble, of course, was the fact that the universe is not just enormous, but it's growing, right? It's expanding. But that's for other sessions. So perhaps the first fundamental discovery made using galaxies by these people was the fact that the universe is enormous. It contains much more than the Milky Way. The way Hubble solved this problem was not by building models of what the universe could be. He solved this problem because he had a very big telescope, I think the biggest at the time, the Mount Wilson telescope, and he had a calibrated relation, which he didn't really understand properly at the time, but it was there, an empirical relation that allowed him to have a standard candle. So technology and looking at the data, this is how Hubble solved the problem. Going forward, of course, today, you can see Andromeda in exquisite details, and we are confronted with new questions. And of course, probably the biggest question that comes to mind when you think about galaxies is dark matter. And this is Vera Rubin and Andromeda. And of course, as you all know, what Rubin did was to measure rotation velocities in Andromeda by using the Doppler effect. And so, as you all know, the point of this story of dark matter in galaxies is that the rotation curves are too fast. Velocities are too fast in comparison to the amount of baryonic mass we see inside. This is Rubin's and Ford paper about the flat rotation curve of Andromeda. And what I want to do in the first few minutes of essentially the material in this talk is I want us to look at Andromeda and some other galaxies and analyze this data in a very pedestrian way, something that any high school student can do. Even inflationary people can do that. And I want you to really look at this, and I want you to understand at the level of the numbers, where is dark matter in this story? Okay? And that's not a completely trivial task, but in the end of the day, it's simple. So there will be no black box, no galaxy simulations, no nothing. We just put some numbers in. First thing to say is that around 50 years later, after Rubin and Ford, the data of Andromeda is still very consistent with essentially their measurement. without very big changes. I'm taking this data here from this SOFU paper from 2015. There are many, many other compilations. I'm not trying to be particularly precise on what data set I use. The answers are not going to change a lot. So these red points are points that I just digitized and put from this SOFU paper. I also put a distance scale very roughly in kiloparsecs. And here the y-axis is the velocity. Okay? So how does this look like compared to the data? And I urge you to actually, if you don't work on galaxies, or also if you do, take a few minutes, go to the SIMBAT database, look for M31, and look at some of these pictures to see for yourself what's going on in here. Okay? And so this is Andromeda. Again, I'm putting a distance scale very roughly by eye on this plot. And here is the Rubin and Ford, or later data from SOFU, the velocity, the rotation velocity of matter in this disk as a function of distance. And what I want you to notice is this Rubin and Ford data extends all the way to around 30 kiloparsec. And if you compare it to actually the picture of Andromeda, this is essentially where you see stuff. Okay, this is the distance where you essentially see matter. Actually, it extends further beyond what you can see in this picture from SDSS, I think. However, the data that we have today goes out much, much further in distance than the data of Rubin and Ford. The arrow bars that I'm putting here, again, rough arrow bars, are from the same paper, and they include systematic dispersions between different tracers. I'll talk a little bit about this later. There are measurements, if you just want to measure the mean and not really the dispersion between different probes, there are measurements that are much more accurate, much more precise also, of these velocities, but they're consistent with the numbers I'm showing. So I also zoomed out on the picture. This is 300 kiloparsec. And so we have velocity data way out of where you see anything. And this is done using globular clusters, satellite galaxy, and gas that can be seen much farther away from where you see the stars of Andromeda, but it already gives you an idea that this tiny little speck of light in the sky is actually affecting matter at enormous distances outside of it. And most of this area is dark. You don't see what's going on in here. So I like this picture. And now, astrophysicists try to understand dark matter in systems like Andromeda, and they coin various terms. One of them is this R200 and M200. Here in this paper, they try to quantify what R200 is for Andromeda. Let me just tell you what is the definition. So the point is that the density, you try to model the rotation velocity, and then the density profile of your fitting model calculated at R200 is equal to 200 times the critical mass density inferred essentially from cosmology or from Hubble, from velocity divergence, from Hubble measurements. Okay, so that's a definition of R200. And this R200, the distance where the mass attached to this speck of light drops to 200 times the cosmic average. This distance is around 200 kiloparsec, and I put it in the circle here. So again, to the point, this object is mostly dark, but the tiny speck of light is sitting on an enormous overdensity of mass, and only here on the circle it drops to 200 times the cosmic average. It's still way up on the mountain there. Now you can do this exercise very easily. You don't need some fancy analysis, so let's see it. If the motion is essentially circular, then the circular velocity squared is just gm over r, where m is the total mass enclosed in the object. This is for a spherical distribution of mass. Of course, the stars are not in a spherical distributions. There are small corrections to this problem, but are not very important and certainly not important at large distances. So this velocity should connect to some mass over radius. And I can put the numbers in. And OK, so what I can do, I can take just the velocity at 200 kiloparsec here, 150 kilometers per second. That's where I put my dot. And R200 is 200 kiloparsec. Kiloparsec is around 310 to the 21 centimeters. This is G Newton in CGS. So if you put the numbers, you find around, I didn't round the numbers, so you don't think there is some magical 1 in there. So there is 1.04 10 to the 12 solar mass. You don't need some fancy computer for this. You can put the numbers yourself for Andromeda and any other galaxy, and look, this is perfectly consistent with the estimates that people give. And the statement about the density being at R200, 200 times cosmic mean, it's also something you can check. What does it really mean? For example, does this definition depend strongly on what you think is the matter density profile in Andromeda? Well, it does not. It depends a bit, but not much, because we just calculated M200 directly from velocity. So if I take M200 and divide by the volume of a sphere with R200 radius, I just put the numbers again. I find 10 to the minus 21 at 29 gram per centimeter cube, which is, when I divide by 200, which is cosmic mean. So this rho 200 is quite robust. You're not very sensitive to the detailed definitions. So we have a proof here that this dark region is actually full of mass. Another natural, very basic question you might want to ask, I definitely asked myself, is where does it end? So we've seen that there is this dark region. Where does it actually end, the region of influence of Andromeda? There are many discussions on this, on how to define it. I'll just give you some very intuitive ones. For example, you could ask yourself, we're talking about rotational velocity, supposedly, at these distances. Well, how long does it take for a test particle or a star or a gas element to complete a full circle at this distance? We know the velocity, so the time is 2 pi r over v. So if you put the number for R200, the number is around 8 gigayear. Not much smaller than the age of the universe, actually. If I go back a factor of 2 out, the number I get is 16 gigayears, which is longer than the age of the universe. So the stuff that is measured here, it's not really on a circular orbit. And if it had been, it had not had time to complete a full circle. Okay, so just to understand where we are in this picture. Another definition, potentially, of where does the galaxy end is when is the next house. Okay, where are the neighbors? This is from the movie Neighbors, which I haven't watched. Well, the nearest massive neighbor of Andromeda is us, the Milky Way. Our distance is around 800 kiloparsec. And so whatever the region of influence of Andromeda is, it's truncated by another galaxy at distances of order 800 kiloparsec. This distance is a bit shorter than the typical distance that you can estimate that should separate massive galaxies, assuming galaxies make up all of the matter mass in the universe. Okay, so there is a neighbor usually. Another amusing effect that would cut off the effect of the influence of the central mass from Andromeda is in fact cosmic expansion. This connects to Luca's lectures. So our universe today is on large scales dominated by dark energy. Dark energy leads to something that looks like de Sitter expansion from our point of view. And you can calculate, if I put a galaxy, a point mass, in the de Sitter background, then it's a calculation you can easily do. There is an exact metric solution for this. It's called Schwarzschild de Sitter. You can calculate orbits in it. If you do the calculation for the orbit, you find that the angular frequency for rotation is modified. So GM over R cubed will be just the Newtonian result. But there is in GR this correction from expansion with h naught, the local velocity divergence, the Hubble constant. And so expansion also truncates the influence of galaxies. And in fact, velocity squared is not really GM over R, but then there is a truncation radius that you can estimate. And for Andromeda, I roughly put the scale here. It's around a megaparsec. Okay, so also Hubble expansion truncates these systems. And there are other definitions, like virialization radius, that are more complicated, and I won't talk about. So this is roughly where it ends. And we are here to discuss fundamental physics. We are here to discuss, for example, dark matter. So what about dark matter? You've seen that this system is dark. You've seen that it's full of mass. Why do we call it dark matter at all? Could it be just gases? Could it be some baryonic element? And to settle this question is not trivial. In fact, a first look at it, or the first answer you often get, relies on things like stellar population synthesis, modeling of the radiation of stars. And you want to understand how much mass is there in this bright component there in the stars. And that's really difficult. So from the same paper, I'm showing a table with different models. Every little object here is the name of a different stellar evolution model that tries to simulate the way the stellar population in Andromeda is built. What type of stars are there? How many of them are supermassive giants? How many of them are white dwarfs or compact remnants, etc., or ordinary G stars? And the thing to point out is that if you look at the predicted mass to light for different stellar models, for example, this one, which is the main model used by the people in this paper to derive statements on Andromeda, then you find some numbers, for example, mass to light in the green band or in the infrared band, mass to light ratios in terms of in units of the sun's mass to light result. But if you look at other models, you can find easily factor of 2 differences between them. And as is stated clearly in this paper, there is really no a priori at this time, no first principle agreed upon a priori calculation that can actually tell you which one of these models is correct. So yes, we see the stars, but we don't really know how to weigh them to a factor of 2. Okay? So how much of the mass here is really what we call dark matter and how much is stars? I would comment that for Andromeda, gas is a small composition. It's not very important. It's really the stars. Luckily, to answer the question of dark matter, or to see evidence for dark matter, we don't really need to know which model to trust. And the point is that these people here, they also show to you an analysis of the surface brightness, just the distribution of light here in Andromeda. And the line that I put here, the yellow line, encompasses the region in which 95% of total light is contained. And you don't really need a fancy model to say where all of total light is contained. It's just where the light is. I also put the same line on the picture. So what people often do, and these authors did the same, if you want to be conservative and you don't want to commit to some complicated model, what you can do, you can try a model that is called maximal disk. This is the model that they're showing here. Again, on the y-axis is rotation velocity, and here it's distance. This is a zoom in, and this is large scale, same plot on very large scale in radius, logarithmic, and this is linear. And you can see what these people did. This here is the observed rotational velocity. The dotted line is the contribution to rotational velocity coming from stars in their models. And what they did, they just took the contribution from stars and crank it up as much as they can, so it just saturates the rotational velocity at the inner point. This simple exercise is called the maximal disk. This is within a factor of 2 or so from what the stellar evolution models are predicting. And it's a conservative way to see what's going on, because then the rest of the curve is to a good approximation nailed by really the observed distribution of light. Okay? So we can have an upper bound on how much mass the stars can really give. And you see that the rotations are way higher, and at large distances really way higher than what the stars can give in Andromeda, or the baryonic mass can give in Andromeda. You can put the numbers here at around 30 kiloparsec. According to this maximal disk idea, dark matter and baryonic matter are roughly comparable in contribution to rotational velocity from Andromeda. So wherever we actually see the matter, it's of order 1. And at larger distances, you see here at around 300 kiloparsec, there is a factor of 3 difference. Now, as I said before, Gm over r is v squared, so m is proportional to v squared. If you have a factor of 3 in velocity, then you have a factor of 10 in mass. So there is around a factor of 10 more mass in dark matter than in stars, observed in this rotation curve, without committing to some fancy or complicated, important, yes, but complicated stellar evolution models. Okay? So around a factor of 10 more dark matter than baryonic matter in this circle, just from the data. I should say this is probably an underestimate to some extent, because the stars are in a disk, and the dark matter is thought to be more or less spherical, and disks affect the rotation velocity farther away than the simple 1 over r prediction you have for a spherical system. Okay, so we're slightly overestimating how much stars there are there. Good. One small little comment, because you have many talks here about the large-scale structure. How does this thing fit into the big picture? And here is an example of a galaxy survey by SDSS. So how does this picture fit into this one? Most of you probably know it, but it's striking to see this with your eyes, that there is such huge separation of scales between these problems. So what I want to do, you can see this galaxy survey, galaxy density as a function of redshift in Sloan. And you can ask yourself, a distance of 400 kiloparsecs, the diameter of this region of influence, let's call it, how does it look like here? So I can ask 400 kiloparsec today, how does it map to 400 kiloparsec at some high redshift? This is just moving distance. I can do this calculation. What I really want is to calculate a small segment in Z, and I want to do it, in fact, near Z that is very close to 0. And close to 0, that's the step in Z that you have, delta Z, to cover 400 kiloparsec. I do not have the resolution to show this on this map. If I take roughly a factor of 2, I show a distance that it's about the diameter of a circle that's about 2 times larger than the R200. And I zoom in into this picture. I can put this tiny little dot that roughly marks where a galaxy fits. Okay, so galaxies really are tiny little breadcrumbs on these enormous dark halos that are moving around. There is a separation of scales. The question of bias, how these little crumbs of light track the dark matter, is an important and delicate question that Matteo commented on, and there is a lot of discussion that you probably see. So that's just to refer to large-scale structure where we are. Now let me switch in the other direction. We looked at a disk galaxy or a spiral galaxy. Let's look at one of the famous dwarf spheroidal galaxies, tiny little system. Here the scale is roughly 1 kiloparsec. Again, I put it roughly by eye. This is the Fornax dwarf spheroidal galaxy. What do we learn about these? Just from data. And here life is a little bit more complicated, but simple enough that I hope you'll understand everything when I finish this tiny little calculation. So first, you want to ask yourself what is actually observed. And what is observed, roughly speaking, are two things. First, there are line-of-sight velocities. Fornax is close enough that thousands of massive stars are seen individually by various experiments, and you can measure velocity dispersion or velocities per stars and velocity dispersions for populations of stars. That's the thing on the left. I digitized some paper. You can digitize your favorite paper and get your points. The conclusion is not going to change significantly. And what you really measure is line-of-sight velocity dispersion, so the component of the velocity of the star that is parallel to your line of sight to the galaxy. And here's the data for Fornax. Another thing you measure, which is going to be important, is the surface density, the number density of stars in Fornax as you go away from the center. This is from DES. And I put some physical scale here because this is an arc mean. So the shaded region is of the order of 2 kiloparsec, roughly, if I got it right. And you can see that what they do, they map the surface density or the number density of stars per unit square arc mean here. Okay, so you have these two basic observables. What are we going to do with it? This is not some simple rotational velocity. These stars seem to be moving in a dispersive way. They're moving in all directions, so it seems. And so analyzing them is a bit harder, but I want you to take this little exercise just once in your life if you're not really working on it. So what can we say? Well, stars are conserved to a reasonable approximation if you look at the correct population of stars. And so they're conserved in phase space. And this means that the phase space distribution function f, the advective derivative on it, on a trajectory in phase space, if you focus on a small element of position and velocities in the stars, and you ask how it changes in time, well, the number of stars around this volume element doesn't change in phase space. So that's just the Liouville theorem here. And if I write it down like that, it becomes a Boltzmann equation, collisionless Boltzmann equation. There is 0 on the right. I'll get in another lecture to what happens when there is not 0 on the right. And I can simply play with this a little bit. These are stars. They're not relativistic. The Cartesian momenta are just m times v, proportional to velocity. The momentum change is just coming from the gradient of the mean Newtonian potential phi. And so I have this equation that you all know. Let's actually get dark matter from this equation in Fornax. We'll do it in just a few steps. First, we'll take a moment of this equation. That's what we always do with the Boltzmann equations, because there's too much information in F. Right? F really tells you the distribution of all velocities at any given point. You want to calculate some mean objects, so we're going to take a velocity moment of F. And I can do this velocity moment of F. My definition of the distribution function F, I show it an example in here, that integral over all momenta of F at some point is proportional to the number of stars around that point. Okay, so if I take a velocity moment of this equation, I have this. If you think of the physics of what's going on here, here I have a time derivative of the momentum flux associated with these stars. Here, if you took the trace of this equation, you would have an equation for the spatial gradient of energy density, kinetic energy density in stars, and so on. And here is the force. That's the equation that we have here. Now, we are going to inevitably need to make some assumptions to get simple physics out of it. All of the assumptions I will make have been questions in the past, and it's important to look at questions regarding these assumptions, but let's make them now to get a rough estimate. First, we'll assume steady state, so we kill the time derivative in our equation. Then we're going to assume spherical symmetry. As an approximation, this is certainly fine. To 10%-ish level, also this confirms Formnax is roughly a spherical system. Of course, it's not exactly a spherical system, and you got to be careful. Also, this confirms that it is not exactly spherical. There are ellipticities there, so probably triaxiality. And to model them becomes very complicated, but we'll assume spherical symmetry. Then if you change coordinate of this equation, I'm saving you this part of the exercise to do at home, and you get a radial equation of this kinetic energy density related to motion of stars in the radial direction, and the velocity dispersions in different directions. Okay, so all I'm doing is taking this term and moving to polar coordinates, just to make it completely clear what every term means. What is VT and what is VR? For those of you who haven't thought about it, suppose there is some center of mass. We are looking at some region with stars. This is the radial coordinate. And here I can put up a plane, which is, how do I do it? Something like this. A plane which is transverse. So radial velocities are velocities in the radial direction, and tangential VT, tangential velocities are velocities on this plane that is perpendicular. And these are two-dimensional vectors, yes, at any given point. And so what this Boltzmann equation is telling us is that you actually care not only about the radial velocities, but also about the tangential velocity at any point in this object that you're looking at. Either way, so the difference between them is usually parameterized with this function beta, which is just the relation between tangential and radial velocities. Again, to recall, v tangential is a total velocity, or total speed actually, in the two-dimensional plane perpendicular to r. So if beta is 0, then it means that the total dispersion in the radial direction is the same as the total dispersion in the tangential direction, composed of both components. Okay, so if locally the dispersion is isotropic, this beta is 0. This is what people mean when they say isotropic velocity dispersion. If you put this together, you get the Jeans equation, which is not due to Jeans. It's because, like Jeans, it comes in many shapes and sizes. Only some of them are used. It was derived by Maxwell, but applied to astronomy by Jeans. So this is the Jeans equation that you can derive from these two things. And another very short step you can do with a pencil and a piece of paper is to show that if you're lucky and the function beta is constant in radius, it doesn't need to be, but let's make our life simple in this way, then you can simply write an integral solution for this object, the kinetic energy density related to dispersion in the radial direction. Now, this object by itself is not directly observable. Nevertheless, we have an equation for it. And the cute thing about this equation, here on the right, you have n. N is the number density of stars, three-dimensional number density of stars. And m is the total mass inside some radius r, m of r. And M is essentially the model of the mass model you want to test with the data, and N is observed. Well, a projection of it is observed by DES, for example. So that's a good equation. You have to supplement it with an equation of what you actually measure, the dispersion along the line of sight. So if this is this little volume element I drew before with Cartesian coordinates, and we live here, and we see the light coming from here, what we want is the dispersion projected on our line of sight, V loss, which the amount of radial motion compared to tangential motion differs if you look at different parts of the galaxy with a fixed Cartesian coordinate system, like the one I drew before. So you can do the geometry. This is the expression using beta to convert velocity dispersion in radial direction to observe the line of sight velocity dispersion. And now we have a closed set, or well, in this model, a closed set of equations because I made some simplifying assumptions. And here is the point. This object is not directly observable. However, number density of star is constrained. I can solve for this object, plug it in the integral, make some assumption for beta. I is the column density of stars, okay? Just the line of sight integral of n. So it's also constrained by observations. And I can calculate and map to observations. That's a process. It's a two-step process. Let's see how it falls apart in here. So as I said, the number density of stars constrained, for example, by DES in this galaxy and other galaxies. It's important for the exercise. For example, one of the lines here is a Plummer profile. I chose it just because it's simple. You see, none of the lines is a perfect fit to what we see. It's just a parametric fit of what we see. But if the stars are on a Plummer profile that roughly fits the data, the 3D number density looks like this, and the integrated luminosity, or the surface brightness, looks like this. So you can plug these expressions into the Jeans equations. The second thing you want is, of course, the matter density. Let's make it simple and just look at dark matter first. And I'm going to just choose some parameterized model for what dark matter might be doing, motivated by the results of cold dark matter numerical simulations, ignoring baryons here. This is just to test the model. So this is the NFW, the famous NFW profile, and I write this model here. If I write this model here, I have a model for M that I can finally compare to data. Let me do that. You can calculate what M is, plug some numbers that I get by trial and error, and just fitting by eye what we see. Simply putting these things into the integrals, I get the line of sight velocity dispersion of Fornax with an NFW profile. These numbers are not some fancy fit coming from a black box. It's literally what I just did by eye in a Mathematica notebook. You could only do it, and I suggest you do just once in your life. And so the different lines, dashed, dotted, and solid, are different values of my constant beta that I'm assuming. You can see that velocity anisotropy, if it's constant, doesn't make a huge effect on large radii, but it's important in the inner part, and it's a significant uncertainty in the modeling. This is not dark matter yet. I model Fornax with dark matter, but I need to know a bit more. I also need to know about baryons. Before that, let me just go on with this model a little bit more. First thing I'll ask is, what is R200 of Fornax? Just plugging in this form, roughly I can directly get the number. It's around 16 kiloparsec. And I wanted to make where 16 kiloparsec is clear in my presentation. So here is again, this is where the stars are, 1 kiloparsec. This discussion of R200 is discussion about stuff happening here. Far out, more than a factor of 10 outside of where you see the star. Again, we have a tiny speck of baryonic mass in an enormous dark halo. And we can also calculate what is the mass inside of these regions. It looks like the mass inside of R200 is in the ballpark of 10 to the 9 solar mass. Different fits give slightly different numbers. How much baryons are there in Fornax? As far as I know, there is no detection of any gas associated with Fornax, only stars. We are back to the thorny problem of calculating from stellar population synthesis how much stellar mass there is. For example, this paper says that there is about 4 times 10 to the 7 solar masses in Fornax in stars. You can take it with a grain of salt of a factor of order 1 probably, factor of 2, maybe 4. Anyway, if I use this number, I get that what I obtain from velocities, the total mass inside of 2 kiloparsec over here, is roughly 5 times larger than the mass in stars. So you need a lot. You really do need a lot of extra dark mass to satisfy these measurements. If I'm very brave, and I'm taking seriously my mass model all the way to tens of kiloparsec distance, I'm getting into mass-to-light ratios in the tens, and for some dwarf galaxies, I will get hundreds. Enormous amount of dark matter compared to luminous matter in these dwarf galaxies. But I stress, this is coming from information far away over here, or from extrapolating the model. Okay, I'm really pushing it. I'll just make a small comment about there is an enormous discussion on core versus cusp in galaxies, essentially because this NFW model from the 90s seems to indicate a cusp behavior in the center. I refer you to the huge literature on this. I'm not going to jump into this discussion. I just want you to look yourself at what it means to have a cusp like NFW profile to fit the data, or a core. Okay, here I did exactly the same exercise, but with a different model of dark matter that is cored. It does not have a 1 over r cusp. It approaches a constant core. And you can understand for yourself that why this is a complicated, thorny question, because getting this information from observations is hard. Not at all saying impossible, but very hard. So there could be a large difference in the distribution of mass in the inner part, and it will hardly be reflected in the line of sight velocity dispersion. Okay, this I will more or less skip. That's just the third galaxy and the last one in my list. Slightly more complicated to look at. It's a disk galaxy, and it's called low surface brightness. It doesn't seem to have a bulge of stars. It does have a lot of gas, and analyzing the gas presents challenges and also important opportunities to constrain the mass in galaxies like this one. Whichever way you do it, wherever you see the stellar matter in this problem, just to explain, where you see the starlight here is roughly 2.5 kiloparsec. So starlight ends around here. But there is more data. And here the mass to light ratio, the dark matter to baryonic and gas mass, is about factor of 3. Okay, so again, more dark matter than baryonic matter in this galaxy. Okay, so I think I'll try to finish on time and push other material to the next lecture. The bottom line is, we look at galaxies. You don't need a black box. You don't need a fancy simulation. Well, you do. You need all of that, but not to understand the evidence for dark matter as a rule. We see evidence in essentially every galaxy we look at where the measurements are clear and robust to some extent. But of course, we don't know what it is. We don't know what it is because the whole beauty of gravity is that if you put a rhinoceros on an orbit around some mass distribution, or you put an apple, they are going to move on essentially the same geodesic. And so the possibilities for the mass of dark matters are enormous. The parameter space is enormous. It's not a very well-defined problem. We have no idea what the mass of dark matter is from particle physics point of view. You will hear many talks that try to understand or to cope with the possibility the dark matter is somewhere not so far from the weak scale. I think this discussion is very motivated. It's motivated by the fact that we look at this table of content of quantum field theory, the standard model. It's very natural to ask what happens if we add another state X, another field X, which is kind of similar to all of these other guys, that interact with similar strength, has weak scale mass, and so on. That's the broad motivation for me to think about this range. And then you have an enormous amount of different ways that you can try to look for it. There are indirect and direct ways to try to detect it. I leave all of this to Tracy Slater and other people next week, I think, and I will not touch on this at all, because I think it's very important to consider the possibility that none of these methods will work, right? It would be lovely if dark matter is WIMPs with weak scale cross-section, but we can't seem to be finding them so far. And so it's possible that all of these methods, well, they are, I would say, very speculative with an enormous possible gain. But it's possible that none of them is going to be able to capture what is really going on. So how can we really make progress? I'll skip all of this for another time. Well, a question you should ask yourself is when I show the parameter space of dark matter, there was a lower bound in the ballpark of 10 to the minus 20, 10 to the minus 21 electron volt. It's a tiny number in particle physics standards. And there was an upper limit of in the ballpark of 10 to the minus 10 solar mass, an enormous number in particle physics standards, some 80 orders of magnitude in here. But how come I even have a lower bound and an upper bound? Not a trivial question at all. The answer we do in both cases is because if dark matter is so light, or if it is so heavy, then we should see something by gravity alone. And what it should do is gravity, yes? I mean, this dark matter should explain galaxies, should explain the CMB. Gravity alone is enough to make bizarre situations that we can see. So I am naturally going to be led to these corners as opposed to the center, where just with gravity, there is something we can learn. And specifically, I will focus on galaxies for this. So in the next lectures, I'll talk about ultralight dark matter, which is essentially the idea that dark matter may be here. And specifically, what can we do if you're not lucky? Dark matter doesn't talk directly to the standard model, and we just need gravity alone. Second thing I will do is go back to data and think, how can I go to beyond mean field? Because the honest truth is that I'm lying when I say that rhinoceroses and apples behave the same. Very massive objects behave slightly different, and we'll see it. And the last thing I'll try to cover is gravitational lensing. Okay, thanks.
So presumably, could you explain why the line-of-sight velocity dispersion would be potentially a more useful observable as a tracer of dark matter density profiles than just looking at the rotation curve and trying to fit the model?
Oh, it's simply the thing that we have for some systems. So it's a very good question. Why am I even wasting my time talking to you about velocity dispersion? And all of you seen when I try to derive it, that the derivation is more complicated, that we run into assumptions, spherical symmetry, time independence, all this stuff. Some of these assumptions actually also are relevant for interpreting velocities of disks in terms of just v squared equal gm over r. But others are unique to dispersion systems and definitely more complicated. I don't know the velocity anisotropy from first principle and so on and so forth. So why to use it? The answer is because that's what I have for many systems. And moreover, it looks like that's what I have for many systems that are very dark matter dominated, like these dwarf galaxies. So they are very interesting to try to understand dark matter there. So I use what I have, and I try to show what is simple enough. There are other traces that are more complicated. This, I think, is simple enough that you can even try to break down some of these assumptions and study them.
Okay, thank you.
Thank you for your talk. At the beginning, you said you explained the definition of the R200.
Yes.
And if I understood it right, we have the density distribution, which goes down to 200 the times of the average density in the universe, more or less.
That's a definition.
And
yes.
How do we estimate it if we don't see, for example, the dark matter? Because yeah.
Okay, great. Thanks. How can I? Okay, there is no skipping this, I'm afraid. Well, okay, I won't go there because the system is refusing to let me. So here it is. What the exercise I did is the following. Just from the rotational velocity, in a simple assumption that the matter distribution is roughly spherical, this assumption is motivated by the answer, which is that dark matter dominates at large distances. So otherwise, there is a small geometric corrections. But with this assumption, I can simply get the mass from v squared equals gm over r. Right? So at any given radius, I can just get the mass. right? I know what r is because I'm looking at that radius. From v squared, I get m. Good. Then the exercise I actually did in the slides, you can look later, is to take the m value I got and divide it by 4 pi over 3 times the r I got cubed. And this is now density. I have the value of the cosmological density from cosmology, not from galaxies, but from cosmology. So I can ask at what value of r, this completely observable quantity, rho divided by r cubed, at what value of r is this number reaching 200 times the cosmic mean? And this is ignoring any geometrical effects, and it gives you the answer that the sophisticated simulation paper is giving you to a very good approximation. So to a good approximation, you can simply directly from the data find this out. It's roughly model independent. Did I answer your question?
Yes, thank you.
Does it work? Yes, great. Very good. So, good morning, welcome back. This is the second lecture, and I proceed according to this scheme. And we arrive more or less to this slide, which is also a quick summary of many things that I said yesterday. And it's something that will appear more than once later on. We could be interested in studying something that modifies gravity, it's just one particular form, or one of the most interesting and simple to explain. And we say that this actually can depend on many things. This constant, this parameter beta strength and the range lambda, which now I rewrite in terms of the mass of a field, because that's what I want to now go into quickly, and then we take our time later on to go much more into that direction. For now, I just want to make an example of this. So why could it be that this effect is actually not universal, in the sense that it could depend on where you are and what exactly you are observing? And this is a simple example of that. It's called the chameleon mechanism. And so let's now imagine there is a scalar field, so dark energy cosmological constant is a field. This will be detailed and studied much more in depth later on, but just to think of a field now. And then if that's so, then this m is really the mass of the field. That's is the first quick way to see this modification. There is a field. This field interacts with matter. So it's a fifth force, effectively. It's a low energy fifth force. It was a question about the low energy deviation from standard model. That could be one. And then, in that case, you define the mass of the field through the second derivative of the potential. But this potential now is not necessarily a minimum, at some point I draw somewhere there. So it's not as simple as the mass that normally you define in particle physics, because there's not necessarily a simple minimum of the potential. So the mass will actually generally depend on the field phi, because if you are rolling on over this potential, you're not sitting on the minimum, then the second derivative is actually a dynamical quantity. So you have to solve now. So in general, this m of phi will depend on phi. And what is phi? Well, let's imagine a structure, which could be a star, a galaxy, could be any structure, intentionally very generic now. So if you want to obtain a configuration of phi, you have to solve a kind of Klein-Gordon equation, except there's no time, but there's only distance, position, r, radial distance. So imagine a static configuration. So that's essentially is a spherical static version of Klein-Gordon equation, a second-order differential equation for your field. And now you have to define an effective potential, just because if the field is actually interacting with matter, there will be interaction terms, which can be written in a simple case in this form. That's not very important for what I want to say. It's just that in general, since this depends on phi, you want to know how phi depends on position around the structure, and therefore you have to solve a Klein-Gordon equation for that static and spherical configuration. If you solve that, you might have a situation such that the mass depends on phi, that depends on r, so the mass depends on r, and maybe the mass is very large up to some distance and very small above that distance. In that case, you have a large mass here to some scale, so this term is negligible, and then a small mass later on in the sense of distance, farther away from your structure. And then you have that this becomes perhaps unity, so you have a modification of gravity. The quick summary of this slide is simply that if you think in terms of a field, and there's not a simple static ground state like for a potential with when you're sitting in a minimum, then many interesting effects, new phenomena can appear. For instance, that you introduce a force, but this force is screened below some distance, perhaps up to near the size of your star or your galaxy, and is modified only beyond that, which means we could live in a situation in a particular we could live in a situation in laboratories or in the solar system or within the galaxy, and there you will not see this force, this extra interaction, but you can see it beyond the scale of the solar system or the galaxy. So that is another simple way, actually a very interesting one, a very generic one, to show that it's not enough to measure gravity locally, but you really have to do cosmological experiments, because there's always the possibility that these new effects are screened locally and can be seen only at large distances. We'll come back to this later on. All right, so that essentially concludes what I wanted to say yesterday with this last slide. And now we go back to the obvious question of how to observe dark energy or cosmological constant. And the idea already mentioned several times, we have a relation between flux and luminosity. Therefore, we can get the distance if you know the luminosity, measure the flux. And then what you have to do is you measure flux, you get the distance, and from this you make some statistics and you get cosmological parameters. Now, of course, the question is, how do we ever can be sure that there is something with a luminosity, which is the intrinsic luminosity, intrinsic luminosity is how much energy the source emits per second. That is constant, because or constant, at least that you know, because you want to know this. And the idea is, of course, the famous, the important idea of standard candles, which has already actually been mentioned a moment ago. The idea is extremely simple, intuitive. If you observe lights and you know they're all more or less the same, and that's, of course, is the crucial point. But in some cases, we can imagine that the sources we observe are the same, in the sense of physically similar objects. Then, obviously, if the source is very bright, that means you receive a large flux, then you immediately know that this is closer to you than something which is much dimmer. So that's the whole idea, to find something that we are kind of sure, or we can reliably assume that emits the same luminosity because they belong to the same class of sources. Then in this case, we can apply this formula. And the idea is to use supernovae as 1A, a particular kind of supernovae, as standard candles. I'm sure those that do cosmology are very familiar with that, but maybe the others not much, so let me spend 2 slides on this. The idea written in this astronomer-friendly form is to know or to have a way to calibrate or measure this absolute magnitude. And the closest thing we have to standard candles nowadays are these kind of supernovae 1A, which are simply white dwarfs, which are the end stage of the evolution of many stars, including the Sun. And they will live together forever if they were isolated, because they reach they burn all the nuclear fuel, and they reach heavy nuclei like carbon and oxygen, which require too much energy to be fused, so they stay there and would simply spend their life without ever changing their configuration, except if they're not isolated. If they're even a system in which there is another companion that can lose matter, in particular if it is a red giant, which is a very fluffy object and can easily, as a very small surface gravity, can easily have a leakage of matter, which is attracted by the white dwarf. The white dwarf will accrete mass, and at some point the equilibrium between the degeneracy, between the electron degeneracy, pressure electron degeneracy of the white dwarf and gravity is broken. It's a complicated series of events that transform this peaceful white dwarf into a monster, into a supernovae 1A. Now, this is the idea why we expect that this strange situation will give rise to a standard candle is just because of the famous Chandrasekhar mass, which depends only on fundamental constants. Of course, I cannot give you now, I cannot spend all the time to study the theory of supernovae. I just want to give you some rough indication. So we could expect that there is a standard candle here, standard candle mechanism, because the point at which this equilibrium between the electron degeneracy pressure and gravity is broken corresponds to the Chandrasekhar mass, which depends on universal, apparently, hopefully universal constants, like the mass of the proton, and therefore should be the same everywhere, this 1.4 solar masses. So the idea is that there is an object which, once it reaches 1.4 solar masses, explodes as a supernovae. Then we expect that the amount of energy which is emitted in this explosion is related to this 1.4 solar mass. It's a fixed fraction of that. So that's a rough idea of why we expect this strange phenomenon to have a threshold which is independent of where they are, whether they are nearby or farther away, and therefore they should emit an amount of luminosity which should be a constant. Now, this of course is just a theoretical expectation. In order to be sure that this is what happened, you have to calibrate. That means you have to first select a number of supernovae of that kind in the nearby universe, and if it is in the nearby universe, you might know the distance already by some other tools. So now you use this equation in the opposite way. You know the distance of some source because they are relatively local. You measure the flux, and then you can infer the luminosity. That's the calibration process. Once we are sure that all the supernovae are the same kind, so that we can classify as 1A, and I'll discuss in a second what 1A means, but once we are sure that they belong to the same class, and once we verify locally that they indeed have the same luminosity, we now start extrapolating this, and we say, okay, then perhaps, possibly, all the supernovae in the universe have exactly the same properties, because if those in the local universe have, then maybe they should be the same everywhere. So it's a mix of theoretical expectation and, most importantly, local calibration. Without the step of local calibration, we cannot just rely on the expectation due to our theory of white dwarfs. Even because we're not even sure that all supernovae 1A comes from this simple process of white dwarf accreting. So now one of the crucial points from astronomers is, well, how can I identify a supernovae 1A from other kinds of transient objects in the universe? Fortunately, supernovae 1A have a characteristic spectrum which distinguish them from other kinds of supernovae, and in particular they have no hydrogen lines and a strong silicon line. Without even asking ourselves why this is so, it's an important question, of course, but it's more astrophysical, the fact that there is a class of sources which have a characteristic spectrum that you can see, identify easily from all the others in the rest of the universe is enough to define a class, even if we have no idea what that would correspond physically. We identify a class, and we can proceed with this local calibration and then extrapolation to the rest of the universe. Now, why they have no hydrogen is interesting, and that's the reason why we think they are white dwarfs, because white dwarfs burn all the hydrogen, and the richer situation which they have only carbon and oxygen and traces of heavier elements. But even if we didn't have too much of that information, we could still use a class of well-defined objects and see whether they happen to have a constant luminosity. Now, the many good properties of supernovae, one of them is visible in this collection, this gallery. Now, I don't know if you're familiar with that, probably many of you are, but the impressive thing of this plot is that this is supernovae, this is the galaxy, this is supernovae, this is the galaxy. You might see even by eye that the brightness of the supernovae is more or less the same as a galaxy, except a galaxy lasts for billions of years, a supernovae only lasts for 1 month. And I remember a World Cup, since it's been mentioned, a World Cup, in which somebody said, a sportsman, I mean a football player, I tell you, I heard that with my ears, and I like to repeat that. Yeah, you know, a World Cup only lasts like a supernovae. A World Cup lasts as long as a supernovae. That's exactly true. A supernovae lasts 1 month. But this has been mentioned by a player, and I don't know why. I mean, so it's a kind of pop culture. You can say a World Cup lasts as a supernovae. That's correct. So even football player know about this, you know. That's very interesting. I don't know if I heard that in a few years ago. I don't know if they've been repeated in this World Cup. Okay, and that's exactly true. The light curve of a World Cup is essentially 1 month from the moment you start seeing it to the moment to which is now too dim to be visible any longer. So in this month, the supernovae can reach a point, a luminosity, the peak, which is essentially the same luminosity of an entire galaxy. Minus 19.5 is the typical luminosity, or minus 20 is the typical luminosity magnitude of an entire galaxy, except it lasts for a few days around the peak, while the galaxy lasts forever. So you have a class of objects which are as bright as a galaxy, with a typical spectrum that you can easily distinguish from others, and that you expect to be standard candles. Unfortunately, they're not standard candles. These are light curves of different supernovae, and they have a peak which is not really the same. Actually, the entire light curves are not the same. To be a standard candle, you will have a universal luminosity, because you need to know the absolute luminosity, but it's not universal. It goes from minus 19 to minus 20. For years, that was a problem, until in the early 90s, clever people realized that there is another observable a bit hidden there, which is the width or the length of this World Cup tournament here. This supernovae is shorter. This supernovae here takes more time. In a sense, you can think of this supernovae as bigger, in some sense, having more luminosity. So it takes more time to reach a maximum. It takes also more time to decay. And this one is shorter. So by using this extra information, you can tell whether the light curve of a new supernovae that you finally observe and you don't know anything about, whether it is of the short kind or of the long kind, and therefore you have a luminosity or magnitude which is not constant, but, that's important, is related to another observable, the width of this light curve. In other words, you can define you can stretch this light curve and obtain a universal one. And now it's so universal that indeed the scatter around the peak is just a fraction of unity, which is a small, around 19.5 plus minus 0.1 or 0.2. Now this is universal, which means if I take any supernovae in the universe, of which I only know the flux, the little m, I will have a light curve which has an arbitrary normalization. I scale it until I find this, scale it and stretch it until I make it overlap with this, and therefore I can read what is the absolute magnitude. Is always around minus 19.5. All right, so this means that supernovae 1A, although not standard, are standardizable candles, and that is what matters. Even if something is not standard, if you can connect the luminosity or other characteristics to another observable, then you can use that to infer the absolute luminosity. With that, people could realize the first cosmological Hubble diagrams. An Hubble diagram is a diagram in which you put distance or redshift on one axis, z, and distance. You see this m minus little m minus capital M is essentially 5 logarithm of d. So it's essentially a distance. You call it a distance modulus. So it's distance versus recession velocity, z. This is what you call a Hubble diagram. And since we know that z is related to scale factor, related to the distance, we can say is luminosity versus distance. That was realized in 1997, and just you see a few supernovae are a cosmological distance. This is the local universe up to 0.1, and this is the distant universe, redshift toward the unity, where cosmology really matter. Otherwise, you just measure the local expansion rate, the h naught. Then, a couple of years, 1 year later, people extended from 7 supernovae to roughly 40 supernovae, and then a few hundreds, and then today, the order of 1,000 supernovae. This is the biggest Hubble diagram that you can realize. There is some update recently, but it's not so important. So, magnitude versus redshift. And now, it's a question of statistics. You can see, perhaps, in the next plot, which is this one. Now the question is purely statistical. You remember we wrote down the R of Z equation yesterday, which is an equation that contains all our cosmological information. Is essentially the integral of the Hubble expansion. And this contains our cosmological parameters, omega mater, omega lambda, W, lambda, and other things. So we can have a theory of that, and I simplified assuming a flat space. And now we can compare that, and again this m minus m is just 5 logarithm of this r times a factor 1 plus z to define the luminosity distance. So that's the theory. That's the theory. You can predict this modulus, distance modulus, and plot it along with your data. And now that's the Nobel Prize picture, because people discovered that a simple universe with omega mater equal to unity and no cosmological constant, this one here, the second line, is almost systematically, almost always below what you observe. Below means the supernovae are systematically dimmer than you would have predicted in a universe with only matter and no cosmological constant. Dimmer means that the luminosity distance is likely longer than we would have predicted in a universe without a cosmological constant. And you can play with other models and try to get the best fit. That's what we do all the time in order to measure cosmological parameters. Now this can be easily seen by all this idea of how distances change and time scales and distance scales change with the expansion can be easily seen by this in this slide. This is the log-Hubble law. We know everything about this, but only depends on h naught. And this is what I like to call the global Hubble law, which is simply the distance as a function of area. It's the same expression. I wrote it there. That's what cosmology is. Now, very simply, if h in the past is smaller, which means there is acceleration, because h is the velocity of expansion. So if it is smaller in the past, it means we are accelerating. Then r of z is large. Of course, this is smaller than is large. Larger distance make dimmer supernovae. That's all it happens. We need to have larger luminosity distance, so we need to have larger a and smaller h in the past, which means acceleration. So connection is acceleration gives you dimmer sources. If the sources, of course, have the same luminosity, they don't change intrinsically, change only because of distance. You can also see in terms of time, is even easier. If you plot AT as a function of time, the expansion factor, this is a decelerated universe. This is a universe which is initially decelerated, but then becomes accelerated, which means the curvature A double dot as this form rather than this. And they, at the time of today, you want to have the same derivative, because that's what we measure, is the expansion rate today. So fixing the derivative today, I can compare this expansion with this expansion, and you see immediately that the age of the universe, which is the time scale, which is almost an identical integral, except there is a factor 1 plus z multiplying a denominator that doesn't play a big role. The time scale is automatically larger for a universe which has a period of acceleration with respect to a universe that doesn't. which also helps to solve the residual age problem of the universe, to make it longer enough to contain stars and old stars and globular cluster and things like that. But it's another story. All right. So then you can start playing with statistics. And for instance, you can start with the simplest possible model. Only matter and cosmological constant and curvature. Curvature has to be 1 minus the other components. So there's only 2 parameters that really define the entire cosmological model, at least in the last 10 billion years, forgetting about the radiation epoch. So your G depends on 2 parameters. Well, in general, depends on many parameters, but in this particular case, depends only on 2, omega matter today and omega lambda today. And the reason why it depends only on today is because we assume we know what these 2 components were doing in the past. Matter was pressureless and just go like 1 plus z cube, and the cosmological constant, and the curvature goes to as this effective dependence. So you can do the obvious thing you will do from laboratory 1, that is, you have your data, you want to fit it, you minimize some chi-squared or some likelihood, and depending on how many parameters you have to minimize with respect to the parameters. So that's exercise that brought these people to get a Nobel Prize, of course, completely deservedly, because the problem was not to make this little exercise of statistics, but to collect this data, which was extremely difficult. But once they collect the data, this exercise could be done by any student, because it's really just a simple chi-square minimization varying with respect to some parameters. Now, there is an interesting way to look at this, which is the following. You can take this distance and ask yourself, for a given z, which value of omega matter and omega lambda give the same distance? Let's call them isodistance lines, which are the locus geometrical figure in the omega matter, omega lambda plane that gives you the same distance for a given z. Because if there is such a geometrical figure, then it means, since the distance is the same, that you cannot distinguish that omega matter and that omega lambda along that line. There will be isodistance. So if you play this, then you can draw these 2-dimensional lines. And these are lines of constant luminosity distance. Along this line here, for instance, omega matter varies, omega lambda vary, but they vary in such a way that they combine to produce the same luminosity distance. So that line is a degeneracy line. You cannot ever, if you have a measurement at that redshift, you cannot ever distinguish a point that is here from a point that is there, because it gives you the same distance. And this, for instance, is at z equal 1. But fortunately, you don't have to make measurement all at z equal 1. Fortunately, you can do measurement at many values of redshift. If now I go to the extreme redshift of order 1000, which is the CMB redshift, then I get also isodistance line, but they are very different from those, actually almost orthogonal. This direction is almost orthogonal to this direction. And even at z, this is only for z equal unity, but supernovae, the important ones, the cosmological ones, are indeed around z equal unity, but actually go from 0.5 to 1.5. So they're not just exact lines like this. I have one line like this, another one which is similar but slightly tilted, another which is slightly tilted, and I can get observations in various regions. Still, most supernovae indeed are around redshift equal unity. So I should expect that whatever statistics I measure, I will not be able to distinguish very much points in this direction. In fact, that's exactly what happened. If I make a statistical analysis of supernovae, I get a confidence region, statistical confidence region, which is elongated in this direction, just because this direction is an intrinsic degeneracy line of the entire problem. Fortunately, however, I can do observation also, for instance, from the CMB, as imagine Fabio will explain, and in that way, I can get a confidence region which is almost orthogonal, or anyway different from these two. And that is what saves us from this problem, because I'm again probably the first showing this plot. I'm sure it will be shown by it's amazing. I have a record showing 3 plots that I think for the first time. Anyway, that's the point which explains 2 of these 3 observations. The third one is actually even simpler to explain. I'll discuss in a second. Qualitatively, of course, But amazingly, it's that simple. So the reason why we should have expected, even before starting doing observation, a situation like this, well, we could not have predicted that they were crossing in one place, but certainly at least two must cross somewhere. We could have predicted almost without doing any calculation that we should have obtained regions like this. Of course, how big the regions were, that depends on the data. But that's exactly what we should have predicted. A confidence region, which means points, parameters that fit the data from CMB in this direction, points that fit the data from supernovae in this direction. And now there is a third line, which is large-scale structure, BO. I'm sure will be mentioned by the speaker, but they also will mention something about it. And this is almost vertical in lambda because this has to do with large-scale structure, so clustering of galaxies. And the effect of lambda is not particularly strong from that point of view, because what really matters is the content in matter. So this line we could have expected would have been, should have been almost vertical, almost regardless of omega lambda, and that's in fact what we observed. So omega matter is found to be around 0.3. And now we could have expected this three direction, but we could not have predicted the fact that they cross in a place. If that lines were there or there, that would have a big enigma, a big problem for cosmology, because we would have got different values for omega matter, omega lambda that are inconsistent with each other. Unfortunately, statistics can hide this problem. So sometimes Bayesian statistics gives you a result, actually not sometimes, every time, gives you a result, even if the separately, the various observations you combine are inconsistent with each other. But in this case, that's not, that didn't happen. They really are consistent with each other, individually and together, and they cross in a point, which is our famous concordance or standard model with omega matter 0.3, omega matter 0.7. So now I have to cut short this because that will be actually content of various other talks, CMB and things. And that's, again, is the summary of most observations today from supernovae, from CMB, and from large-scale structure, and they cross in a place there. Now, this is the simplest case, lambda. And of course, it looks such a simple exercise that literally can be done by practically high school student once you have the data, because it's just, after all, a simple minimization of a chi-squared. I'm sure in high school nowadays they do even study, as far as I know, statistics, and they do even something like that, so could really be done by a high school student. And so they did it, not just a high school student, but all of us have been doing this for years. So why just two parameters? Let's put three parameters. Let's put a W instead of a W minus 1, right? The one we chose a moment ago. Or maybe four parameters. Why a constant W? Maybe you put a constant and a derivative. It's the well-known Chevalier-Linde-Polanski parameterization. And et cetera, et cetera. Of course, you can do that. And every time you get some interesting result. For instance, this plot, which you have WA and W naught, and they cross near a place which is the standard cosmological model, 0 and -1. So of course you can do that, but it's interesting because making a phenomenology analysis of data is always teaches you something, but there's something missing in all this, of course, if you proceed this way. And there are various missing things. This parameterization of W, including the constant W, are simple, useful to make analysis. Why not? But they're arbitrary. You can invent any kind of parameterization, you always get an answer from your Bayesian or not Bayesian, from your chi-square minimization. But the other more serious problem is that this WZ face value only specifies the background, but doesn't tell you anything about the perturbation. So when you perturb the universe, so you go away from homogeneity and isotropy, do you have the same W, or there is something changing it? It's not obvious. You are not specifying the full covariant Lagrange. You only specify, you only make an ansatz, a parameterization, your equations of motion. So it's not a covariant statement what you're doing. You don't know how to expand it in linear or perturbation, or even what is worse, at nonlinear level. So it's only part of the story. You have to complement it with that. So in other words, you can say this idea of just changing the equation of state does not correspond to fundamental degrees of freedom that we know should appear in every fundamental Lagrange. That means fails. That's why the rest of the two lectures, this one and the next two, will deal about fields rather than arbitrary parameterization of the equation of state. Now, everything is a field, right? Apparently, unless they are strings. but we know something. So we are not really in a such dark place as this slide. We know something about this. We know that there are some observation requirements. So whatever you invent, whether fields or not fields, we want to keep isotropy of the universe because it looks like it's very much isotropic. We want to add a field, or whatever that is abundant. We're not talking about changing by 5% or 2% the expansion of the universe. We are talking about something that, if it is a cosmological constant, accounts for 70%. And if it is not a cosmological constant, it looks like it also should account for a large quantity, because if you want to revert from deceleration to acceleration, you cannot just do that by changing some little sneaking and tweaking a bit some parameter. You have to insert something which is very abundant. And then you want to have a slow evolution, meaning that with W equal -1 exactly, rho is a constant. Rho is cosmological constant is a constant. If W is not exactly -1, rho in principle can be anything, but since we know that is a good fit, the cosmological constant that the plot I showed earlier, everything you want to replace it with will also have to have something which is not too far away from a constant evolution for rho. And then we know that there is a weak clustering of whatever you add, because if you add something that clusters a lot on the scale of halos and galaxies, then they will be counted in the dark matter sector, not in the dark energy one. And we should see it and weight it using the method that we've seen in the previous lecture. Numerically or quantitatively, this means that isotropy, that these four conditions for overall very qualitative, general, fundamental, basic condition will imply something. Isotropy implies that you should use a scalar field, which is automatically isotropic. You could also use as a field a vector field, but then you have to play either with time-like vector field, which do not change the space directions, or with triples of vectors, so it's much more complicated. So I'm not excluding that, but I will not spend time on the possibility of a vector form of dark energy. The scalar field looks like a perfect candidate, also because we know that it exists in physics, and we know that it should be invoked also to explain the other acceleration, the inflationary one. So let's start with that. Large abundance means that omega dark energy, whatever that is, has to be close or actually a bit larger than omega matter, cannot be just a small change. Slow evolution means the W effective, whatever is the W effective that really gives the acceleration. Given a field, you know everything. When you reduce to the Friedmann-Robertson Walker metric, you can define a W effective. So not start from W, but obtain W. And that will have to be anyway close to -1, at least today. And weak clustering means, for instance, that the sound speed of this field, the waves at which this field propagates, should have a sound speed which is over the unity, over the velocity of light. Otherwise, they will start clustering on small scales. So these are the general four conditions. And how do we insert fields in physics? Well, we insert fields using Lagrangians. As we know, this is the standard Hilbert-Einstein Lagrangian to obtain equations of motion. And now we can invent Lagrangians. There are essentially two laws for Lagrangian cooking. You have to form a scala, so equations are covariant, and there should be no explicit functions or coordinates. Coordinates should be inserted in the field, but not as explicit functions. So energy momentum tensor is conserved. So I can invent a crazy Lagrangian written in this way, in which instead of R, I put a function of phi, which is a scala, so the scala times scala is a scala. It's a scalar combination. All of these are scalar obtained in some strange way with derivatives, with many derivatives. So I can certainly invent, I can certainly derive from this nicely looking classical, let's not try to quantize them for now, and nice looking equations of motion. And that will depend on many parameters. Maybe there is some parameters here, there is some coupling constants everywhere. Whatever parameters I put into the Lagrangian, I will find them out in my equations of motion. I derive a R of Z and go back to the observation and produce more and more complicated plots with 2, 3, 4, 5 parameters, but at least each one of them will have a motivation in terms of fundamental Lagrangian. Although, of course, this exercise seems a bit without any end, but still, that's the way we want to proceed, at least. Let's see how we can restrict this class. But the idea is simply that if we want to insert a new field in this Lagrangian, we can do so inventing terms of this kind. There's another tool we need in order to proceed, which will not be needed really very much for what I want to say, but just to be sure that we are not missing one step. Once you do this, then what you want to do, although I will not do that in detail, is take the equations of motion and take two limits. The first one is the homogeneous isotropic universe, Friedmann equations. The second one is little linear perturbations on top of homogeneity and isotropy. And that comes to the second magic tool, is the magic of Fourier space, because when you start perturbing, you cannot assume any longer that things only depend on time, but that depends on space. And that will be a mess in your equation because you introduce terrible coupled higher order partial derivative differential equations. But if you linearize, you can make a Fourier transformation and separate the time dependence with the space dependence. And this is not arbitrary, because Fourier theorem tells us that you can always decompose a function like this into a sum of terms like this. And instead of taking all this, and the sum will be parameterized by the momentum wave number, wave vector k. So let's pick one of those elements in the sum. And the point is that, and then if you do so, then all the operators that you find in your equation will be simply written again as an overall factor depends on time, or the space operators at least, and then as simple factors of the plane wave. So why is this useful? Why is this complication is actually useful? Because it's a linear system. Since the question, if we linearize them, so I take the limit is limit number one, homogeneity, limit number two, linearization, so small perturbations. In the limit, equations are linear, we force them to be linear, and therefore all these factors there simply disappear from your equation. They appear in every single term, and therefore they can be factorized out. And you are only left with equations which contain only derivative with respect to time, and the space part is entirely contained into a wave vector k. There's only one problem with that, of course, that you have an infinity of these wave vectors. So you have an infinity of equations. But they are linear, ordinary differential equation, because there's only time operators, only time derivatives, no longer space derivatives. They have been included in these overall factors. And the second point is that although it depends on k, and there's an infinity of k you should consider, small scales, large scales, intermediate scales, then in most cases you can easily find the solution which is good for all the large scales, or for all the small scales, or maybe something in between. So although you have in principle to deal with an infinity of ordinary differential equations, then actually in practice you only solve them in two or three limits, essentially large scales, small scales, and you discover that they either don't depend on k, or they depend on k in a very simple way. So we trade an impossible system of partial differential equation into many ordinary differential equations, but they can be decomposed, they can be studied separately as a function of k. I didn't mention the most important point. You get an infinite number of equations for k, but they are all decoupled from each other. So every single value of k gives rise to a set of coupled equations which is different from another value of k. That's because we are in linear theory. All right, so these are the two tools you need to use in general. Using this, you can free your spirit and invent theories of possible dark energy models based on something that looks like fundamental physics. There is a scalar field. We write down all possible combinations. And this has been done. People started with the obvious choice, just canonical kinetic energy and potential. And then why not couple this field? So it's actually a new force coupled to gravity. Then something like this is the version of Brans-Dicke. And then something like that, why just a canonical kinetic energy? Let's make a function of this kinetic term, and so on and so forth. And of course, you start multiplying things forever. And some of these have names. People created quintessence is the simplest case. You remember, I started with Aristotle's quintessence, and has been rediscovered 2,000 years later. Scalar tensor, this class of theories, kinetic dark energy, or quiescence, Gauss-Bonnet, and KGB, and other names like this. There's also a KGB version, which has a story behind it, but it's some political content, so better not to go into that. Right, so the idea is that you can go this way. This has been done. It's very interesting, produce many insights, but there should be a limit, and the limit has been found First many years ago, and then rediscovered relatively recently, not so recently by now. The limit of this game is the Hordensky-Lagrangian. In fact, it has been shown that there is the most general four-dimensional scalar field theory with second-order equations of motion can be written in a form which, although complicated, is actually finite. You cannot go creating beyond other terms, except for a couple of exceptions. So these four terms, these four Lagrangians, which can be added, produce all the viable form of scalar tensor, in the means a theory of gravity which includes a scalar field and a tensor field, the metric, that give rise to second-order equations. And you see that there are lots of high-order terms. This is a box times derivative operator to square, so how many? There are 6 derivatives somewhere here. So you might expect, well, put 6 derivatives in the Lagrangian, I get a mess in the equations of motion. How comes it's only second order in the equations of motion? Because each higher order terms that comes from every single individual term cancel out with the others. So this combination is frozen. If I change this 3 to 3.1, I will not have this cancellation, and then I will break this second order requirement. So this Hordensky-Lagrangian is a magic Lagrangian that contains the most general second order equation of motion. This has been discovered many years ago by Gregor Hordensky, that then left, he was a mathematician more than a physicist, and then he left physics for a while. He's a great painter. His painting is, he devoted many years to painting. They produce beautiful painting, in my view. It's a pity I cannot show you one, because I guess I don't have the copyright, so, but they're really beautiful, I like them. But anyway, he produced this just as a mathematical in a mathematical paper. He just asked himself, with no particular fundamental reason, let's write down the most general Lagrangian, which produce second-order equations of motion. And then people was exactly looking for that. In fact, they found the answer exactly the same question, then realized that actually the answer had been offered many years before. Now, this theory has many properties. In general, well, up to some definition of this free function. By the way, I didn't point out this is a completely, this K, G3, G4, G5 are completely general functions. If you have a nightmare tonight, invent a G3, which is a function of phi x, you are sure that you can take your function, put it there, and get the equation of motion, which have the right properties. So they're completely free function of phi and of the kinetic term, which is phi mu, phi mu. So there are free functions, so you can put in infinity, it's an infinitely free Lagrangian in some sense, although it's restricted in form. In detail, you can still have lots of possible choices. But every choice you make up to some general condition, you discover that these do not contain classical and not even quantum instability. So the energy states are bound from below. And of course, in general, it modifies gravity, because there's plenty of terms like this one or this one, this is G mu nu, is the Einstein tensor, that couple to the field. So the matter, there is matter somewhere, matter will feel a force which doesn't come just from G mu nu, but also from the field. So it's a scalar tensor theory, it's a fifth force, it's an interacting theory, you can call many ways. And includes essentially all the models which people have studied separately in the past. For many years, people studied Brans-Dicke, and now it's just a little corner of this. Is the corner without this L5, G4 doesn't depend on X, then you recover Brans-Dicke. Standard gravity, it means that the G4 is unity, and all this is absent, and you get over standard gravity. And interesting, this is also some interesting properties of invariance and under conformal and disformal transformation. Still a couple of minutes, or okay? Well, I cannot resist the temptation to show you this plot. Number of citation of this paper by Hordensky. 0, 0, 0, 0, 0, 0, 0, bump. And I know the story that at some point a friend of Hordensky was in a meeting, a physicist was in a meeting, and in this meeting somewhere in the States, everybody was talking about Hordensky-Lagrangian, and he called his friend, you know, they're talking about your work. What are they doing? It actually didn't realize that. It became so interesting. They realized only after this explosion of interest that people started discussing the Hordensky-Lagrangian in so many papers. So it's an interesting situation. It's an interesting case of a work that produced results 40 years later. So message is, don't despair if your paper is not cited. All right, so maybe stop here. Maybe it's a good minute to stop. Okay, thanks. Thanks. Oh, no questions. Come on. Yeah, a question there.
Okay. Thank you for the lecture. I have a question. I don't know if it makes sense, but you said that for the isotropic condition, the easiest way is to consider a scalar field. I know that there are some works, like in inflation, that regards inflation, that consider instead the vector field. And if you take like a combination of the different components of the vector field, then you can recover isotropy.
That's correct.
Are there works considering vector dark energy in this direction?
Yes, correct. As I briefly mentioned, that's a possibility. In fact, Hordensky invented the most general vector form Lagrangian, which generalizes electromagnetism and still produces equations which are consistent. So he did that. That also has been rediscovered. And now there is also some paper which people plays with vector field, Lagrangian based on vectors. Either you play with a vector which is only time-like vector, so essentially the space part plays no role, so it's consistent with isotropy, or you play with a number of vectors that make a kind of isotropic triad in the sky, and so that again is consistent with isotropy. There are many papers on that, and they produce results which are qualitatively similar in the sense that they produce a range of possible models based on vector Lagrangian that can also explain the data, and they can also introduce some other properties of interaction with matter and things. Yes, there are for some reason they're less studied, I guess just because they're a bit more complicated. You have to ensure this property of isotropy, while with the scalar field is automatic. So yes, the answer is yes. It's also models based on tensor Lagrangian, so massive gravity and double metric Lagrangians, which introduce a new metric, and that also could in principle induce acceleration, but they have so strong constraints that I'm not aware really of successful models, but I'm sure there must be somebody around that would contradict me and say, no, my model is very successful. But I work a bit on that, and at the end I was slightly disappointed not to find that tensor viable theory of dark energy. I hear, but I guess the other people cannot. I can repeat your question if you want.
Thank you.
Okay.
Thank you for the talk. Actually, you mentioned that maybe the Hordensky theory doesn't have ghost. Could you expand a little bit about it?
Yes, I will. In the next 2-3 slides. So maybe it's better to wait. But yeah, and I qualified this. I qualified saying that you still have to impose some general constraints, but they are very general, like some functions to be positive or something like that. While if you try to really go beyond and invent other terms, you will get an unrecoverable kind of instability. With the Hordensky Lagrange, you can. I will mention some reason of why second order is good and higher order is bad.
So thanks for the nice talk. As I understood from what you said about Hordensky theory, I assume I could also say that Hordensky is like the most general inflationary model for the early universe. And based on that, are there any constraints we can use from observables from CMB or similar on early universe Hordensky?
Sure. As you will see, I will discuss that later on. It's already very difficult, or actually, let's say, I really think it's impossible to completely invert the problem. Can we go from data to the Lagrangian? I think we cannot. Let's forget about the problem of initial conditions, which are not included in Lagrange. But even if you could forget about initial condition, that we cannot just using data. And the data that we can get from the universe at the present time are much, much, much more than we can get from inflation, which essentially is just the tensor to scalar ratio in the overall spectrum. So I'm rather skeptical we can do much more progress in that direction, except some very general condition, like a potential has to be with some curvature rather than the opposite, some second derivative, and not much more, and even that, and just simplify case. So let's forget about the possibility of really inverting the problem from data to fundamental physics in this context, and I think actually every cosmologist would agree with that. So we have to use other conditions like simplicity or I don't know, Bayesian thinking that less parameters is better than many parameters and these kind of things. And actually we show that there is a way to go, it's a surprising way that we can actually do a lot for density, but exactly because we can measure so many things in the present universe and we cannot at the inflationary level.
Okay, thank you, Luca.
Thanks a
Thank you,
lot.
Kfir. So let's thank both the speakers and let's go for lunch.